Then I'll give you a lot of homework. Yeah. Okay, so on our last class, we did 2.1, and we talked about determinant and inverse of 2 by 2, 3 by 3 matrices. And I forgot to record. So instead of making a video, I decided to go over the materials briefly so that you can have a recollection of what I taught. Plus, you guys were not even classroom in the class. So it's a good opportunity to revisit all the materials.
So this is picking up from 2.1.
2.1. So what you do in 2.1 is we start with determinant of 2 by 2. In 2 by 2, to find the determinant, our life is easy. All you have to do is multiply the right diagonal element in the right diagonal and subtract the product of the elements on the left diagonal. So we do 80. If your matrix 2 by 2 matrix is A, B, C, D, row-wise, then its determinant is 80 minus, oops, draw. Your determinant is 80 minus BC. 80 is the right diagonal. So you always start with the right diagonal. Right diagonal minus the left diagonal. And the inverse is 1 over that determinant of a new matrix. In the new matrix, you switch the position for A and D. So 1, 1, and 2, 2 position, they change their position. They swap their position. And B and C, they don't swap their position. Instead, they just change their signs. So you change the signs for B and C position, and A and D, you swap them. And then you multiply everything by 1 over determinant. In other words, you divide every element in the new matrix by the determinant. This is what multiplying by 1 over determinant means. On the other hand, for 3 by 3, our life is not so easy, but it's not so bad also. If you want to find determinant using the same method as 2 by 2, you need to copy the first 2 columns again next to the third column. So if the original, let me erase all of this. If the original 3 by 3 matrix is ABC, row-wise, DEF, row-wise, GHI, row-wise, then to find the determinant, we need to copy A, B, D, E, G, H. The first 2 columns next to the third column. And then you're going to find the determinants. So we have to start with the right determinant. The first right determinant is AEI. So you multiply AEI, and then you add the next determinant. Our next determinant is BFG. And then you add the next determinant. Our next determinant is CDH. So you take 3 right determinants, and then you subtract the 3 left determinants. Our first left determinant is inside the original function. Sorry, inside the original matrix. CEG, this is our first left determinant. We need to subtract that. Then subtract the next left determinant, which is AFH. Order matters. I mean, it doesn't matter what you multiply first. You can multiply G and C, okay, and then multiply by E. Within the multiplication, the order doesn't matter. But the addition and subtraction, the order does matter.
So the determinant, like when you did A, B, you multiplied them together and then you subtracted it to the product of B, C. Is that what we're doing?
Which one are you talking about? The left or the right?
The left. The left.
Right. So AD means A times D.
A times D. Okay.
And then CB means C times B or B times C.
Okay.
So in the right one, on the right diagonal, you're multiplying A times E times I plus B times F times G plus C times D times H, all those right. and then you keep subtracting all the left. So GEC minus the next diagonal is HAFH, and the last diagonal is BDI. So add all the right diagonals, subtract all the left diagonals. Whatever you get, that's the determinant of 3x3 matrix. This is one way of finding it. But this is not the only way. There is another one. It's called cofactor expansion. So what we do in cofactor expansion is we expand our matrix about one row or one column. Okay, you choose what do you want to expand by. Do you want to expand by a row or by a column? So this example, they expand by a row. So we have A, B, C, D, E, F. Actually, let me write it closer. We have A, B, C, D, E, F, G, H, I. And let me write it 3 times. A, B, C, D, E, F, G, H, I. A, B, C, D, E, F, G, H, I. So here they expand around the first row. So if we expand around first row, whatever you are expanding the element, you cannot use that row or that column, whichever has that element. For example, in ABC first row or first element is A, so we are using A first, so you cannot use row 1 or column 1. So you take your A and you multiply by the 2x2 matrix you see here, the determinant of the 2x2 matrix. So this is 2x2. You multiply by its determinant. So A times EI minus FH. So this minus that. And then you have to subtract the second one. In the second position, we have B. The second position is minus. So you do minus B, and since you are using B, so you cannot use second column or the first row, because B is lying on the second column and first row. So if you cannot use the first row and second column, that means you left to DI and GH. So GF. So you multiply negative B times DI minus GF. This is your second position. And the third position, you add. So first position is plus, second position is minus, the third position is plus again. The alternate sign. So since you are using the third position, that means this time you cannot use the third column. So if it cannot use the third column, the other two is DE and GH. So you multiply by the determinant of DH minus GE.
This is only for a 3x3,
3x3.
not bigger.
For 4x4, you have to do the same thing, but many times. For 3x3, you have to do it 3 times.
Yeah,
For 4x4, you have to do more than 4 times.
right.
So this is second method. It's called cofactor expansion. We are using cofactors. And see all these things, whatever left, we call them minor. So you're canceling the row and column, whatever left to it, they are the minor. So this is second method of finding determinant. But personally, I like the first method. That's easier. Example. So we have an example here. And here, see, I told you the position matters.
Do you get the
So
minor from the other method that you shared first?
we don't care about the minor in that method.
Okay.
The sign automatically comes from your subtraction and addition.
Right.
But here, sign
Minor is the leftover 2x2.
whatever you cancel, besides that, whatever is left over, yeah. So one example is in this one. Here it says, if you cannot remember the position sign, then you don't have to remember it. all I have to do is multiply -1 with the sum of the position. For example, this position here, the C is row 1, column 3, right? So position is 1, 3. So the sign for that position will be -1 to the power 1 plus 3. So -1 to the power 1 plus 3. What is 1 plus 3? 4. And -1, if you multiply 4 times, do you get positive or negative? Positive. So see, the sign here is positive. Minor means whatever you don't use, whatever you do. For example, if you take this one, so you cannot use row, first row or the second column. So the 1, 6 and 2, 5, these are the minors. The determinants of the thing.
You could pick any row and column.
Any row or any column. But you cannot take one element from one row and another element from another column. That doesn't work. You have to take one straight row, one straight column, either one of them. For example, here,
How do you pick what row? Like, you pick a row.
the best one is if you have zeros, pick that row or that column. For example, here, I have zeros, at least 1 0 I have it. So I'm going to expand around either the first row or the third column.
It's because it ends up being less than that.
Exactly, because 0 cancel out everything. So let's do the third column. If you use the third column, that means we have first element is 0, so everything else cancel out. There is nothing to worry about here. But remember, this is plus, this is minus, this is plus. So this is minus and this is plus. The sign always alternate. So this one will be minus, this one is plus, this one is minus. So what's the position for 3? Plus or minus?
Oh.
Plus. Because we have minus, in the middle is a plus. So you start with plus, and then all the position they alternate. Not position actually, the sign. All the sign they alternate. So for 0, it's gone because 0 times anything is 0. So next position is 2, but it has a negative sign. So -2 times, if you cannot use 2, so if you are using 2, that means you cannot use second row or the third column. So if you can't use that, what is left? 2 and 6, that gives you 12, minus, sorry, not 6, we cannot use the 6, what else? 2 and 1. 2 times 1 is 2, minus 5 times -1, which is -5 times into +5. Okay, never mind. -5. And then our third position is plus. So +6. And since we are using 6 on the third position, so we cannot use third row or the third column. So what is left? We have 2 and 3 now. So 2 times 3, which is 6, minus 1 and -1, which is -1. Right? So whatever element, so I pick the third column. So in the third column, you have to go one element by element. The first element is 0. I skip that because 0 times anything is 0. We don't worry about that. The second position is -2. So -2 means you cannot use this second row or that column. So 2, 1, and 5, -1. You multiply it in the determinant. Then you go to the third position, which is 6, but this position is plus. 293, so 2 times 3, and then if I change everything, so 2 times 3 is 6, minus 1 times -1, which is -1. And then that's it, you just combine them. We have -2 times 2 plus 5, plus 6 times 6 plus 1. So 2 times 5 is 10, we get -20, plus 6 times 7, which is 40. Did I make a mistake? Kenyan?
Yeah. 2.5 is,
7 times 2 is 14. Come on. 14. Good catch. And we have 7 times 4, which is 42. 7 times 4. 7 times 6, which is 42. And then we get 28. So the determinant of this matrix is 28. And let me erase all of this so you can see. And if you're not sure, you can verify that using the other method.
and you can also just take it to row and column.
Another row, another
So
column.
you get the same answer.
For example, here, this example is done by picking the first row. So 2 times 3 times 8 minus 2 times 1. So 16 minus 4, 16 and 4. Sorry, what am I saying? 18 minus 2, which is 16. Then the second position is -1, so you cancel that. You get the other 2. So -1 times 6 times 1, 6 minus 10. 6 minus 10 is -4. So -1 times -4, -1. And then we have the last one 0. Everything cancels out. So it doesn't matter which row, which column you pick, you get the same result. So this is the second method. And now there is third method. This third method is for any type of triangular or diagonal matrix.
Triangle.
Any triangular matrix. As long as you have a triangular matrix, it can be lower triangular, it can be upper triangular, it can be left lower triangular, or it can be right lower triangular. Any type of triangular matrix or any type of diagonal matrix. If you have them, the determinant is easy. All you have to do is multiply their diagonal entries. That's it. And when you multiply the diagonal entries, you have to remember which diagonal is it, the right diagonal or the left diagonal. If it's right diagonal, the sign stays same. But if it's left diagonal, like this one, remember we always subtract the left diagonals. So if you have a left diagonal, the sign will change. But if you have a right diagonal, the sign stays same. So for A, our determinant of A is 2 times 1 times -2, which is -4. The sign will not change because the right diagonal stays same. However, another way to write determinant of A is 2 bar inside A. A is inside 2 bar. And here we have 2 times 4 times 3, and the sign will change. It's not absolute, it's called determinant. That's the symbol. Determinant of A is same as the 2 bar. Looks like absolute value, but actually it's not absolute value.
-24.
-24. So when you have triangular matrix, our life is easy. We don't have to do any of the methods we learn. Neither the first method nor the second method. Question.
The determinant of A,
Hmm?
why did you choose the value to want to -2?
That's the rule.
That's
If you have a right triangular, if you have a triangular, so this is a triangular matrix, do you see?
Oh. The 0, oh, okay.
The upper side is all zeros.
Oh, okay.
And this is also a triangular matrix. Because the upper one is zeros. So for any type of triangle, as long as you have a triangle, your determinant is the product of the diagonal entries. But you have to be careful. Is it left or the right diagonal? This is the right diagonal, okay? Right. And this is the left.
You only need to do the middle diagonal.
Middle. And middle is the diagonal. We don't have any other diagonal. The middle thing is the diagonal. Now, so when we use what method? Well, if you have diagonal matrix, it's the product of the diagonal. And if any of your matrix has, if your matrix has any row or any column full of zeros, entire row zero or entire column zero, the determinant is automatically zero. You don't have to find it. You can find it, but you don't have to. It's by default, it's zero. Or if we have two identical rows or identical columns, means the same row repeats twice, either row-wise or column-wise. If you do the exact same things on two rows, on two columns, determinant is zero.
Two identical rows or columns.
For example, oops, A, B, C, D, E, F, A, B, C. We see A, B, C twice, so the determinant is zero. Or you may see A, B, C, A, B, I don't know, A, B, D, whatever. 4 by 4. The biggest one will be 4 by 4. Or if you have anything, if you have any row or any column that has 1 0 or 2 zeros, use cofactor expansion to make your life easier. For example, this one. Our third column, so we have a matrix column wise 2, 4, -7, 1, 5, 8, and 0, 0, 3. Since our last column is 0, 0, 3, we have 2 zeros, so we are going to use cofactor expansion, and all you have to do is take the position and multiply by whatever we did. So here our 3 is non-zero in this column, so we are going to expand around third row, third column. That means we cannot use third row, third column. So we take the 3 and we multiply by the determinant of the minor. The minor is 2, 1, 4, 5 row wise. So determinant is 2 times 5, 10, minus 4 times 1, 4. And the 3 has a sign plus, minus, plus, minus, plus. So 3 has a plus sign. So we get 3 times 6, which is 18. Okay. Any question? Try this one. We have row wise 2, 0, 0, 4, 1, 3, 7, 3, 92. Find the determinant.
Two slashes means determinant.
Right. So determinant of A, you write this way, or you write the 2 bar. They mean the same thing. Ready? Okay. So how do you find the determinants? Go ahead, Andy. Andy, right?
Yeah.
Go ahead.
So if you multiply the 2 times 1 times -2, and then subtract it with something.
This is not a triangular
Oh.
matrix. It's not a triangular because see, if this is triangle, we still have a number here. Triangular means that every other number has to be 0 above the triangular. Bora, go ahead.
And leave us with 1, 3, 3, -2.
Mm-hmm.
Do 1 times -2.
1 times -2 minus 3 times 3, 9. Perfect. See, that's all you have to do. Figure out, you're going to expand around which row or which column.
Which method did you just use? Inspection?
Mhm.
Oh,
You figure out which one is easier. We found that, oh, first row is easier because it has double zeros. So double zero. Because the double zero, we are taking 2. And since you are taking 2, that means you cannot use the first column also. Whatever you are taking, you cannot use that row and that column. And then whatever we have left to it, that's the minor. So we take the determinant of the minor. Any questions so far about anything? No question from anyone? Elsa?
The reason we don't have the alternating positive and negative sign because it's not a.
I mean, we do have it, but we don't have to use it because this is positive, this is negative, this is positive. But 0 and 0 makes everything 0. So we don't even care about the zeros. The only thing we care now is the 2. And 2 has a plus sign. Okay, then I have a bunch of practice for you. Go ahead, try them. Try with your neighbors. Let me give you an exam and then I'll go pray. So prayer time. Gregory, not here. Emmanuel, not here. Christian, not here. Kenyan, exam. Jose, Jackson, Andy, Julian, not here. Kirk, Mehal, Abby, not here. Where's he? Yeah. Origin, not here. Yeah, right. The Christian, Gregory. Okay. So try all 1, 2, 3, 4, 5, 6, 7 of these. Talk with your neighbors, share your ideas. It's a prayer chance. Let me pray and then we'll do them together.
We're doing all of it.
Yes. You can talk with your neighbors.
So yeah, it's like A, B, minus B, C.
Wait, A, B, B, C. Okay, then. So, does that have like every two by two?
Yeah.
Okay.
And then I'm trying to refresh my memory for Steve. I think again, I think that the. If we write diagonals for Steve, then check the. Same with diagonal thing. Rule. For people who kind of talk, these diagrams, right diagonal, and this. He goes up.
Okay. So, B, we would live in by consumption.
Wait.
No.
Second.
C is 0.
C is 0.
Because it has the two identical residents.
Oh,
Thank you.
so two identical rows, 0.
So.
The rack.
You invert the sign.
That's. Wait, it's a left diagonal, right?
Yeah, because the zeros are on the left.
Much easier way to remember. Zeros on the. Left diagonal. Oh, no.
Yeah, those were trying to left, no, opposite.
Don't look at-
That was one.
So he times 4 times 3 and then 8, right? Was that in number 2?
Well, I'm not.
Like D, like D or E? No, for, I'm still working on. Which one is, no,
D.
yeah, I. Back.
That's 3 times 4 times 2 times negative.
Okay. 2 times 4 times 3 times -1.
Yeah.
Okay.
No, for
I don't know.
3 multiply negative 1. For F, negative 1 times. 2. I'm not sure I'm still wrong, but. Because. The column for 1 here is negative. I did negative 1 times. 2 times 7 minus 2 times 5. Negative 1, and then negative 1. Not looking for it. Yeah, I'm not sure. How would you solve it? Maybe you could- That's all right. You can remember, but. This inspection. That's okay, but like I'm trying to focus and I'm coming upon the one, the rule where you have duplicate rows and duplicate row. Very helpful, thank you.
Or did you get negative?
You did. It's like helping you too, yeah.
Did you guys do the last one?
Stuck on half.
Why?
If I cross out, if I do the cofactor expansion method.
Mhm.
And I cross, and I,
Which row or which column you are using?
I was gonna cross out the middle column, or cross out
Row
the top and the right column. But if I cross out the top column and the right column, I'm left with 2, 0, 3, 0.
Oh, it's the top and the middle.
Why do we pick?
whatever element you are using, I mean, what element you are using, whatever row and whatever column has that element, you have to cross that out.
If the one is in the middle column, you cross out the middle column. If the zeros on the right, then you cross out the right. But since it's in the middle, you do the top row and then the middle column.
Wait, I
So
don't-
you said you're going to choose second column. The it has most zeros, right?
yeah,
So if you pick middle column, so you have to cross that out.
yeah,
And in the middle column, the only number you're using is 1, right?
right.
That means 1 is also on the first row, so you have to cross that out. So whatever element you are using, you have to cross out that row, that column.
That's the 2, 5, 3, 7.
So we have, which one here? We know we are going to use 1.
But so I'm looking at the zeros. 1,
So
0, 0.
cross out this way, it will be easier for you. You're just going to use 1,
Why are we leaving that? That
because you need to multiply that 1 by the determinant of your minor. That's the rule. First you pick the row or the column which has most 0.
Yeah.
So we know the second column has most 0. Since 2 of them is 0, 1 of them is non-zero, we're going to use that non-zero number. So that non-zero number
Result here, other than the determinant.
automatically zero. So one is non-zero,
What about
so
if it
it's
had two non-zeros.
here, two non-zeros. Oh, one non-zero, two non-zero, for example, here. So if you use two non-zero, that means you have to do the multiplication twice. One is for this number, so you cancel out this and that. So it's
Yeah.
1 times 2, 0, 7, negative 2. This is what you have, 2, 0, 7, negative 2. And then position, I need to know my position. Plus, minus, so plus. So this is plus,
And go down to 3.
so 3 has to be minus.
Minus,
So when you pick 3, so you cannot pick that and that and that.
it would be minus 3.
No, you have only 1 3.
Minus.
No, come on.
And then, so I would do 3 times 2, 0, 7.
So if you cancel out that, you're left with 2 0 and then 4 0. Like the matrices I'm talking about.
Yeah.
So it's 1 times 2 times negative 2, which is 4, negative 4. And then 7 times 0 is 0. So this is negative 4. Minus, this is everything 0. So 3 times 0, which is 0. So we have determinant negative 4.
Thank you.
But you didn't have to use the second row or second column. You could use the best one
Oh, yeah.
here. The 2.
Yeah.
Or you could use this one. The negative 2. So this and this, they cancel out.
I did the triangle.
Or you can do triangle. See, we have so many options. This is actually a triangular matrix. So just take the triangle. And which diagonal we have, right or the left? It's right, so it's positive. It's right, see, right. It's your right hand. This is your left hand. If you go that way, this is your left hand. If you go that way, this is your right hand. So this is
Oh,
positive.
yeah, it's fine.
Okay, let's see. Starting from the first one. Who would like to do A? Or actually, remember, Jackson, A. No, tell me, what did you write? 3 times 4. 2 times negative 6. And what did you get? 24. Do all of you have 24? The answer is 24. Correct. Kirk, the next one, B. B on the left page. Determinant of A. Really? So you take the right diagonal. What numbers do you have on the right diagonal? This is your right diagonal. What number you have on your right diagonal? So you multiply 5 times 4. And then you subtract your left diagonal. What numbers do you have on your left diagonal? Negative 2 times negative 8. So 5 times 4, what do you have? 20 minus. What is negative 2 times negative 8? 16. And what is 20 minus 16? 4. So your determinant is 4. That's how you find determinant of 2 by 2. Just diagonal, you subtract the right from the left. Jose, C. Nothing is not a word in determinant. 0. White 0. 2 identical rows. Anytime you have 2 identical rows or 2 identical columns, you don't have to find the determinant, it's automatically 0. E10, the next one.
That's a left triangle,
Left triangle.
which is negative. So you're gonna do negative 3 times 4 times 2.
3 times 4 times 2, negative 24. The answer is negative 24. Okay, blood F.
So it's gonna be basically 1 times 2.
1 times. So you're taking this, so you cannot take this 2.
3 times
2 times 7,
5. 3
5 times 3.
is gonna be
14 minus 15. So this is negative 1, right? But what's the position, the sign for this position? Remember, when you use cofactor, you have to use your sign.
yeah. So,
Every position has its own sign.
so it's the final answer is
So this is negative position, so it's negative 1. So this is negative, this is negative. So final answer is positive 1. Cofactor always use its position, I mean the sign. Any question? Now, who would like to do the last one? Jackson.
I think I did it already. Oh, you know, like how.
Mhm.
Why is there like 2x
2x, 2 minus x, right?
minus x?
Determinant 2 minus x times 3 minus x. You're subtracting 4 times 3, 12. And it says determinant will be 0, means you set it equals 0. And you're finding the value of x. So what do you do? Mhm. 6 minus 2x minus 3x plus x squared minus 12. Mhm. X squared minus 5x minus 6 equals 0. That gives you what? X minus 6. X plus 1 equals 0. So 6 and negative 1. And the answers are correct. And we didn't do one part, which you forgot, I forgot, both forgot. It says use it to determine whether this matrix is singular or non-singular.
Determinant 0.
Determinant 0 means singular. Singular. So A, is it singular or non-singular? Non-singular. B, non-singular. C, singular. D, non-singular. And EF, both are non-singular. Do you like singular or do you like non-singular? What do you want to have? Singular, non-singular, because we don't want the determinant to be 0. Why? What happened when the determinant is 0? We cannot, no solution or infinite solution. We cannot use the inverse, but we want to get unique solution. That's our goal. We want unique solution. In order to have unique solution, we want determinant to be not 0. Okay, since we know how to find determinant, that means now we are going to find the actual inverse function. Not function, sorry. Inverse matrix. So again, there are two methods. One is informal, one is formal. The informal one is easier. It's based on the informal method I taught you before, the first method of finding determinants. When we found the determinant, we repeated the first two column next to the third column. So you're going to do the same thing and you're going to do extra. When you find, once you rewrite first two column next to the right column, you're going to rewrite first two row below your third row. So repeat first two column next to the third column. Repeat first two row below your third row. Once you repeat everything, then you are going to find a new matrix based on the determinant of every 2 by 2 matrix we have in this big one. So cross out the first row, first column, they are not needed. And then find the determinant of every 2 columns. The first 2 column, the first 2 by 2 matrix has determinant EI, FH. So you find EI minus FH, the determinant. Then the second pair has determinant CH minus VI. So if you find the determinant column-wise, you have to write them row-wise. If you find the determinant row-wise, you have to write them in the new matrix column-wise. So find determinant in one direction, but write the result in other direction. So we get a new matrix. That new matrix is multiplied by 1 over the determinant of this matrix. So step 1, find the determinant of the matrix. Once you have it, then you need to get the new matrix. How do you find the new matrix? Taking the determinant of every 2 by 2 matrix. Once you have them, then you divide each element by the determinant, or basically you're multiplying 1 over the determinant. So let's do one example. Let's say we have 1, 2, 3, 4, 5, 6, 1, 2, 1. Step 1, finding the determinant. So to find the determinant, we are going to repeat the first two rows, first two column 1 and column 2. So 1, 4, 1, 2, 5, 2. Once we have them repeated, then we can use the, what do you call it? Diagonal. So first diagonal, 1, 5, 1, which is 5. Then you multiply the second diagonal, 2 times 6 times 1. What do you get? 12 plus the third diagonal, 3, 4, and 2, 24. So every right diagonal, you add them, and then you go for left diagonal. First left diagonal is 1, 3, 5. What do you have? 1 times 3 times 5, 15, and you need to subtract them because it's left diagonal. Our next diagonal, left diagonal, is 1 times 2 times 6. So you're subtracting 12. Subtract. The last diagonal is 2 times 4 times 1, -8. So you add all the black ones, subtract all the red ones. The plus 2 minus 2 cancel out. We have 5 minus 15, which is -10, positive 16. So our determinant is 6. Any questions so far? Once you know the determinant, that means we can find the inverse. A inverse is 1 over that determinant, which is 6. And now you're going to find a new matrix. How you're going to find the new matrix? We are going to rewrite everything what we have. So let me erase all these colors. And let me erase all these things. We are going to copy the first 2 rows below the second row. Sorry, below the third row. So 1, 2, 3, 1, 2, 4, 5, 6, 4, 5. Once you copy them down, The first row and first column are not needed, so we throw them out. They're useless now. And then we find the determinant of the rest. I'm going to go column wise. So first one is 5 times 1, 5, minus 2 times 6, 12. What is 5 minus 12? -7. Then the next one is 2 times 3, which is 6. I'm going column wise, but I'm going to write them row wise. 2 times 3 is 6, and we are subtracting 1 times 2, which is 2. And what is 6 minus 2? 4. The last column we have is 2 times 6, 12. And then 3 times 5, 15. So I'm going column wise with their determinants, but I'm recording them row wise in the new matrix. And what is 12 times 15? -3. And you do the same thing for the other ones. So let me change the color to purple. Next one. What? Tell me what to write, okay? I said so many things. Who can tell me the next one? Mehrab, we didn't say anything today. Tell me the next row. So 6 times 1, 6, minus 4 times 1, 4. What do you get? 2. The next one. One times 1, 1, minus 3 times 1, 3. So what is 1 minus 3? -2. The last one in the second column. 4 times 3, 12. And then 6, which is 6. Good job. Now we left just only one more column. Green. So go ahead. Who can tell me the last column? The last row.
8 minus 5,
So 8 minus 5.
3 minus 2,
Wait, 8 minus 5 is 3. And then we have 2 minus 2, 0.
5 minus 6,
5 minus 8, which is really -3. And that's it. This is our inverse. We just have to make it fancier. The A inverse. Where's my black? A inverse is 1/6 times -7, 2, 3, 4, -2, 0, -3, 6, -3. Even though we are done, but we cannot stop here because we have to distribute the 1/6 to every element inside. Exactly. Basically, what you're doing is dividing everything by 6. And you have to reduce that. You cannot stop here. The final answer is what?
7 over 6.
-7/6. Row wise or column wise?
Row wise, sorry. Row wise.
2/3.
Yeah, negative 1/2,
-1/2.
negative, or 1/3,
1/3.
negative 1/3,
-1/3. 1,
1/2,
1/2, 0,
negative 1.
-1/2. Now this is the final product.
What the matrix of that? Why did you cross out the?
Because they're not needed. We don't need them anymore. Just like the expansion, when you expand around a number, you don't take that row, that column. So basically we're expanding it out here. So we're not going to use this or that.
It's always gonna be the top one?
Always the top, the first row and first column.
For this-
Cancel them
For this specific now.
For the inverse of blue.
for this specific method. So this is informal method, okay?
Yeah.
This is not how real mathematicians
It's this one or the
or
cofactor
the
expansion.
cofactor expansion. If you use cofactor expansion, this is the thing you have to remember.
positive, negative, but
Mhm.
they're always, top left is always positive.
Always positive, you always study positive. Positive, negative, positive, and then you alternate the sign. And this is the determinant of the two matrices. So we do the same thing, we did the same thing in our process, but we didn't write explicitly this way. And we didn't care about the sign because the sign automatically comes when you do that method. But this is actually the actual method, the formal method. You multiply every, you take every, what is called, minor, and you take the determinant of every minors for that position. So for one position, for example here, you have A, B, C. So A11, A12, A13, and this is A21, A31, A22, 23, 32, and 33. So for that position, you are taking the determinant of that, which is the exact same thing. And this is plus. Then for the second position, you take this, but you cannot take this or that. So you take the determinant of these two positions. And this position is minus. I find it time consuming.
So you're using full method, like something you came up by yourself?
No, I found it online.
Oh,
And I was like, cool. If I knew during my class, I would have got A in my class. This is the only class I never got A. I did not get A in my linear algebra. We didn't have matrix algebra. We had linear algebra. Exactly. Linear algebra was the only case in my entire life I did not get A. I got C. Not even B. I got C.
so,
I hated this class.
so for like machine learning and AI,
Useful.
you need linear algebra,
Definitely.
but matrix algebra, not that now, like.
Matrix algebra is the baby step for the linear algebra. It's not two different fields. It's the same thing. So linear algebra, let's say this big. Matrix algebra is the first step of your big linear algebra. If we had a linear algebra, I was a student at CCNY. We didn't have any matrix algebra. We had straight linear algebra. And from calculus to linear algebra, completely different. Like, I was so shocked. That was the only class in my entire life I got C, and I never could forget that. Like, man, if I knew this concept before,
Yeah.
I would love it. So, nah, I hate that. Okay, so we did this, we did that. So we are done at 2.1. And 2.2, it's same thing as 2.1. The new thing is few theorems about the determinant. And also you're going to learn how to find 4x4 matrix, determinant for 4x4 matrix. Good news, we're not going to do inverse for 4x4. Inverse for 4x4 is harder.
One over 4x4?
No.
No.
The 3x3 method we learned, we cannot use it for 4x4.
Of course.
The 3x3 is unique for 3x3. For 4x4, we have different methods. Let me talk about it a little bit here. So first method is cofactor expansion, which is harder because first you're going to expand around one row or one column, but then you get 3x3. For every 3x3, you have to find their determinants. Okay, so either you're going to use the shortcut or cofactor expansion again.
Well, if we use cofactor expansion here, we can just take that
Then you have to do
big column of zeros though.
if it's non-zero, then you have to take 3 times. First one that, second one that, third one that. Like, it's a long method. It's not bad, but it's just long. The second one is by inspection. So by inspection means figure out if you have zeros anywhere. If any row, any column has zeros. If you do, then do the same thing, but with only one number.
But I could take this first column, like A21, A31, A41 are all zeros. Or all, this is all zeros, so we only have to do
So
this.
all of them are zero, you only have to do this.
Yeah.
So if you have zeros, your life is easy, but not every matrix has zeros. For example, this one, they don't have zeros. So what we do, since you don't have zeros, what you do is actually something cool. There are two things you have to do. I mean, not you have to, you have choices, two choices. One choice is reduce that into a triangular matrix. If you do that, your life is easy. The product of the triangle, the diagonal is your determinant. Or what's the other method? What do you do? In a column, make all entries 0 except 1. So you have to do raw echelon anyway. So either you make it into a triangular matrix or you convert that into something that has all zeros and one non-zero entry, like this one. All zeros, but one non-zero entry. So if you have all 0, 1 non-zero entry, what you do is you expand around that row, that column. So we are going to expand around 2. So we are going to cancel out this, cancel out that. And we have 2 times, but you have to remember the position. Plus, minus, plus, minus. So this is minus position. So minus 2 times the determinant of this. But one good thing about the small minor is that it has double zeros. So we can cancel these double zeros. So we are taking this number and we do the cofactor again. So this time, let's see the position. Plus, minus, plus, minus, plus. So every matrix has its own position. The position for the first, the 4x4 will not be same as the position for the 3x3. Okay? For 4x4, this 2 has position negative. We cannot say this is negative, this is positive, this is negative, this is positive. We cannot use this method for this one. This is a new 3x3 matrix. For new 3x3 matrix, the plus position is the first one. So plus, minus, plus, minus, plus. Since we're using this position, so 3 is the plus 2.
-2 times 3
So
times
-2 for the first, plus 3 for the second one,
-3.
and then you're left to 5 times to 10, minus 4 times 12.
Oh, my
So 10 minus 12. So -2 times +3 times 10 minus 12. So -6 times -2, that gives us +2. Okay. So this is what we are going to do in our next class. We are going to do this example using raw echelon form. And then we are going to talk about a little bit more about matrix, the determinant properties. And remember, Friday, there is no class.
Yeah.
We're going to meet again Monday. Your review sheet is that, and not review sheet, the exam.
Just take attendance for the online classes, because
I did not.
I wasn't able to attend them because you did it earlier and I have class for this.
That's why I didn't take attendance.
Okay,
Because I want to punish you.
okay.
I wanted to ask about the homework, exam 1 homework.
Oh, the
Great.
email. I was